you hear me?
Yes.
Yep.
Yes. Okay. Hello everyone, my name is Ali Selim. I'm a PhD student at the University of Illinois Chicago. I work with Dr. Ahmed Aboukifa, the director of Swim Research Lab. Today I will be presenting our work about graph neural network-based state estimation of water quality state estimation in water distribution networks. So let's start by talking about the chlorine or water quality management. Water quality degrades due to biofilm formation. For that reason, chlorine is typically used as a disinfectant to maintain water quality and also to prevent waterborne diseases, as chlorine kills pathogens like bacteria and viruses. However, adding more chlorine will not make water cleaner. In fact, there is a challenge to appropriately define or appropriately determine the chlorine dosage, because low chlorine concentration will be insufficient for appropriately disinfect water, and also high chlorine concentration will increase the harmful byproduct like trichloromethane. Advancements in sensing technologies allow us to remotely sense some of the water quality and flow and pressure of water distribution networks. Unfortunately, water quality sensors are typically expensive, so due to budget limitations, we only place sensors at a subset of junctions. And here the state estimation comes to play. The definition of state estimation is the process of identifying a desired variable based on the measurements at a subset of junctions. For example, if we talk about a simple network, if we have two sensors here, the idea is to use the measurements at these two sensors to determine the chlorine concentration at the meaning of the network. And the advantage of doing that is state estimation informed decision making, such as if we are deciding where and if we really need those stations to increase the chlorine concentration at the far end junctions. There are two main approaches for state estimation. The first approach is the physics-based, which the governing equation is being solved to estimate the desired value, such as what we do using Ethernet. And the other approach is the data-driven model, where measurements are used to infer the state of a desired variable, such as what we do in machine learning. So in physics-based models, it requires calibration and optimization, which takes time. And for that reason, it's not very suitable for real-time applications. But the good thing is that it can be applied because it actually uses the physical information of the system we are dealing with. But for data-driven model, it requires training, and once the model is trained, we can simply use it to get the state of the variable we are interested in. And typically, data-driven model runs faster, so it's suitable for real-time application, but it's not very good while dealing with new data. State estimation have been used in water distribution networks to estimate some of the hydraulic parameters, such as flow and pressure, and also water quality parameters, such as chlorine concentration. So the objective of this study is to utilize graph neural network models to estimate the chlorine concentration of water distribution networks. And this will maintain real-time availability. It will enhance estimation accuracy because graph neural networks accounts for the node connectivity, and ultimately we are aiming to build a graph neural network model that is capable of working on any sensor design. So why we are using GNN? Again, GNN takes into account the node connectivity, and it will understand the network topology. If we compare the artificial neural network to a graph neural network, in artificial neural network, it is learning or it's training to predict the output based on the inputs, whereas in graph neural network, it also understands how these nodes are connected together. So how can we explain, or how can we represent a water distribution network into a graph? The graph consists of 4 components, and the junctions of water distribution network will be represented as the node of the graph. Pipes, valves, and pumps will be represented as the edges. The demand, and in our case, the main feature or the main property we are interested in is the green concentration, which would be considered as the node feature, and the pipe lengths and diameters would be the edge feature. In this model, we developed two different graph neural network models. The first one is the static prediction model that simulates the fixed sensor measurements. It only works on a specific sensor design. In other words, again, I'm using this simple network. If we train a model on these two locations as sensors, it can only be used to predict the green concentration knowing the information at these two. It can be used on any other sensor design. On the other hand, the dynamic prediction model, it simulates the mobile sensor measurements, and it works on any sensor design. So if it was trained on these two sensor design, it will definitely be able to also predict the green concentration using the same sensor design, but most importantly, it will also work on different sensor design that it wasn't trained on. So as any other machine learning model, we need data to train the graphical network model. So we use synthetic events, and these synthetic events are simply built by or developed by the determination of two variables. The junction demands, which is controlled by user-defined input for the range of injection demands and the total demand of the network. The other variable is the Green injection rate. The user identified in the model the range of injection rates and also the location of the injection nodes. Once these events are created, we pass them to Winter, which is the Python interface of Ethernet. We get the results from Winter. We do masking, as I will be explaining in a few seconds, to create the training and testing data sets that will be used to train the model, and the model will then be used to predict the green concentration. So I said masking. What do we mean by masking? So in masking, we hide the green concentration information from unobserved nodes. Because in Ethernet, we extract the data for all events. So if an event is represented as this vector, each value here is the green concentration for the junction. The idea is to hide some of the information at some of these junctions. So for example, in event number 1, we consider the J3 and J5 to be unknown, and the objective of the model is to actually estimate these values based on the information at G1, G2, G4, and G6. So each event here is represented as a graph. The node features, which in our case is the green concentration and the flow, is extracted from the graph. It passed to a dense layer to flatten this feature, and then it's combined with the node connectivity, which actually tells which node is connected to which one. These two are then passed to a multiple layer of topology adaptive graph neural network to a dense layer again, which will result in the green concentration we are interested in. The two models, the dynamic prediction and the static prediction models, were applied to seed-tunnel benchmark network. It consists of 388 junction, 429 conduit, and 5 distributed area. As I mentioned earlier, the dynamic prediction model is capable of working on different sensor designs. So to test this, we actually used 3 different sensor designs. In sensor design A, we consider the sensors to be scattered all over the network, and their locations was determined based on the spatial clustering approach. Whereas in DNA and design B and design C, the sensors were only covering a single distributed area. And it's worth noting that design A was the one used in the static prediction model. So looking at the static prediction model results, we see that on the left side, we see a heat map where the green represents low error, and here we are considering the mean absolute percentage error as the error metric, and the red represents high errors. There are 2 main observations we can get from this plot, which that there is a relationship to proximity to sensors and the error. So closer to the sensor, so this black shape represents the sensor location. So closer to the sensor we are, less error we get. And also, we also see that dead-end junctions systematically feature high mean absolute error compared to intermediate junctions. Looking at the one-to-one plot on the right, we see that there is a relationship between chlorine level and reduction error. The high values of chlorine level, in this case it was the values between 3 and 4 milligrams per liter, had a higher reduction accuracy compared to lower values. And this can be seen as the nodes in this part lie on the 45-degree line, whereas in this part it's spreading away from the 45-degree line. We also tested the robustness of the model to noisy measurements. So we trained the model on a noisy measurement following a normal distribution with mean of 0 milligrams per liter and standard deviation of 0.5 milligram per liter. And that was the training phase. But in the testing phase, we applied different standard deviation to see if the model is actually capable of handling the measurement noise. And here we are looking at the results for different level of measurement noise. So although the model was trained on 0.5 milligrams per liter, it was actually able to detect the clean concentration for data with no noise, which I call it as a clean data, and the error were approximately between 0 and 20%. And what we can see here is also increasing the level of noise was actually, of course, increasing the error. But what is more important to say here is that when we compare the graph neural network model to the EBNet, we found that the graph neural network model is actually robust to uncertainty, because in graph neural network model, we are using the data from these 10 points, whereas in EBNet, we are only using the data from the injection source. So looking at the comparison between the prediction accuracy of the static prediction and dynamic prediction model, we see that the overall mean absolute percentage error is 5%. And I mean by overall is actually the average of the mean absolute percentage error of all junctions, whereas for the dynamic prediction model it was 15. So the dynamic prediction model featured like higher errors, and this can be considered as the trade-off between a model that only works on a single sensor design and producing accurate result, and another model that works on any sensor design, but of course will sacrifice some of the accuracy. Here we are showing the influence or the impact of the input sensor design on the prediction accuracy. So again, the prediction accuracy aims to predict the clean concentration for any sensor design, but we are expecting that it's not going to be the same accuracy. For sensor design A, where the sensor was scattered all over the network, the performance was much, much better than only putting the sensor at a certain DMA. In this scenario, we actually enhanced the prediction accuracy in DMA number 1, but we sacrificed the prediction accuracy for the remaining part of the network, and the same thing for sensor design C. So in conclusion, two models were developed in this study, namely the static and dynamic prediction. The main takeaway was that a direct relationship exists between the node proximity and the error. There is also a systematically higher errors for the dead-end junctions, and also the static prediction model outperformed the dynamic prediction in terms of accuracy, but the dynamic prediction model is suitable for sensor placement optimization. Our next step is to account for the dynamic behavior of clean concentration by applying the temporal graph neural network. Thank you so much, and I would be happy to answer questions.
Thank you very much, Lee.
Thank you, Abby.
Thank you. Yes, Linda, please.
Yeah, so when you were making your analyses, were those steady state analyses?
Yeah.
Okay, and secondly, did you look at the any tanks in your analysis at all?
So it's a good question. So in fact, to satisfy the steady state, we had to get rid of all the tanks, because if it's going to fill in,
Right.
empty and fill, it's not going to be steady state at all. So we had to get rid of all the tanks in the network. But this is actually our second, next step. We will be accounting for all these, to account for the unsteady state condition.
Okay, so what problems do you anticipate you might encounter if you throw tanks at the input?
So in this, so actually this is the first attempt to apply graph neural network for state estimation of chlorine concentration. So we just thought that it's an initial point or like a checkpoint before we head further to the real application, which is like an actual network with dynamic behavior.
Thank you.
Sure.
Yes, any other questions? Yes, please.
Thank you for your interesting presentation. I was wondering, what was the runtime for the different models compared to EPM?
Okay, so for the training part, we are utilizing the GPU computation. So for this network, I would say it takes like maybe 30 minutes, 45 minutes to complete. And of course, the prediction time is actually almost zero. So what you can predict for 100 event in a split second. But I expect if we apply the model on a larger network, it might actually reach maybe like 5 hours or even a day. It depends on the size of the network and the number of nodes. Yeah.
Any other comments, questions? Thank you very much.